Hello everybody, today I wanted to make a video detailing how to draw free body diagrams. Given a specific problem, how to set up your free body diagram and what your free body diagram tells you. So first, if you don't know what a free body diagram is, it is just a diagram describing the forces acting on an object. And it's a lot easier to show you this given an example. So let's come up with a problem. Let's say that you have a person pushing on a block with a force of 10 newtons. So let's say we have a 10 kilogram block and then a person pushing with 10 newtons of force. And we'll say that this is a frictionless surface for now. So first thing you draw is just the system. So here's our block with mass M equals 10 kilograms. And then there's our little person over here. He's pushing. So drawing the system like this, and then I'm going to draw an arrow to say he's pushing this way. This is a really simple system, and you might be able to conceptualize this without actually drawing it out. But I always like to practice drawing my problems just because when things get more complicated, it becomes much easier. So now let's draw our free body diagram. We'll say that here's our block with mass M. And then we know that it is touching the ground at this point. Anytime something is, well, let's first talk about the gravity, because unless something is in space or in a, some very specific situation, there is a force of gravity. So there's an arrow coming out of it in the direction of gravity, and I'm going to call that FG. And then that is a vector. Then we'll also say that there's an arrow coming out of the top of it, and then this is going to be our normal force. The normal force is the counteracting force of gravity. So because the block is sitting on the ground and it's not falling through the ground, the normal force has to completely counteract gravity. So you could say that N, that's an M, N equals FG. Because if you were to sum the forces in the y direction, you would get that it is FG minus N. But because it's not moving in the y direction, we know that this equals 0. Okay, so that's our forces in the y direction. And then we know that there is a 10 newtons of force. We'll say that the person is pushing exactly in the x direction. So that gives us our arrow here. This is the force of the push, which we know is equal to 10 newtons. And then this push is going to, if we do Fx, is going to equal 10 newtons. This is where you could apply Newton's law to determine the acceleration of the system. We know that in the y direction, there's no net force, so the acceleration in the y direction is 0. But in the x direction, there is a net force of 10 newtons, and so you can set this equal to the mass of the system times the acceleration of the system. You know the mass, and so you could solve for the acceleration. I'm not going to do that right now, though. I'll post some other videos later detailing how to do that. Right now, we're just practicing drawing the free body diagrams. Okay, so let's practice another one. Let's say that you have, this time we have a block on an incline plane. We'll say that the block still has a mass of 10 kilograms. And this time, let's throw friction into the system. We'll say that there is a frictional force, let's say that the system isn't moving. We'll say it's a static friction. So, static. We'll say our plane has an angle from the horizontal of 20 degrees. So, first we draw our system. Here's our inclined plane. Angle from the horizontal is 20 degrees. Here's the block sitting on the plane. And that's our system. So let's draw our block now. I'm actually going to tilt it to kind of show exactly what's going on. So when you're drawing your free body diagram, it may often help to draw a reference line to know, okay, this reference line is equal to, that represents the plane. It might just help you to think about it a little more. Gravity, as always, is going to point straight down, FG. The normal force is always exactly counteracting the force, the surface force, or the contact force. So it's going to be perpendicular to whatever surface the object is touching. So that's your normal force. And then friction always counteracts the direction of motion. Gravity is naturally going to pull this block down the slope. So friction is going to be this direction. We'll call this F sub S for force of static friction. So that's the end of this free body diagram. So what does this free body diagram tell us? Well, we know that this angle, theta, is equal to 20 degrees. We can use that to calculate how much of gravity pulls in the horizontal direction. In the case of problems like this, I like to tilt my reference frame. So I'll say that this is the normal force. This is the force of static friction. And then gravity is doing something like this instead. We know that from this triangle up here, here is force of gravity, there's a triangle here, this is 20 degrees. So since this is 20 degrees, this angle here has to be 70 degrees. So draw this angle as 70 degrees. You can then use that to calculate how much of the gravitational force is in the x direction and how much of it is in the y direction, just from your basic vector analysis. Another way that you could set up this specific problem, if you wanted to keep your initial angle, is to realize that since this is a 20-degree angle, it forms a 20-degree angle over here. Let me draw it to show you what I mean. So if here's your force of gravity, you draw a line parallel to the plane, and then a line in the direction of, in the y direction. So parallel to the normal force. And then this angle would be your 20 degrees. And that's just trigonometry. That might be a little easier for you to think about, because then you can say, okay, I know that this is my force of gravity, and so this here is Fg sine of 20, because this is our right angle right here. And then this is Fg cosine of 20. And then you can correlate that to over here. If you get rid of your Fg entirely and you instead break it up, you can say, I know that the normal force component, or the force parallel to the normal force, is Fg cosine of 20, and then the other one is Fg sine of 20. And then as a characteristic of equations that or systems that aren't moving, remember this is a static system, Fg sine of 20 is going to equal the force of static friction, because they're going to point in opposite directions and the system isn't going to move. And then the normal force and the gravitational force in the y direction will also cancel each other out. So in general, the whole system doesn't move. That's a very common physics problem to see on your exams. Something like this, and then you're asked to calculate the force of static friction or maybe the coefficient of static friction. So I would familiarize yourself with problems like this as much as possible. So those are two relatively simple free body diagrams and how to draw them. A general rule, given any problem with forces, when you're drawing your free body diagram, as long as you have a vector or an arrow for each component of the force, or whatever is acting on the object, you should be pretty good to go with your free body diagrams. So the ones we did, like we know, there's always going to be a force of gravity on any system. If it's touching something, there's always going to be a normal force opposing it touching that, because if not for that normal force, it would fall through the ground. So say if you have say if your water bottle is sitting on the table, the force of gravity constantly pulls that water bottle downward. But the normal force from the table pushing on the water bottle counteracts the force of gravity and prevents it from going anywhere. And that is how you solve or how you set up free body diagrams.